Hello everyone, today is my Studies in Network Aided Learning Systems paper presentation 2, and my title is Adaptive Quantum Fast-Wave Programming with Surprise and Forgetting Mechanisms for Resilient Sector Rotation, and I'm presenter Min Kai Hong. Let's start off with our motivation. First thing is non-stationary financial dynamics. Financial markets are non-stationary, noisy and time-varying, with rapid shifts in liquidity and risk structure. And traditional portfolio models rely on unstable correlation estimates and lack cap- capacity for high-dimensional dependency modeling and lead to high variance, unstable out-of-sample performance. And second is the limitations of DRL in finance. DRL directly maps market states, which is portfolio weights. And however, value-based RL suffers from curse of dimensionality and temporal credit assignment under sparse rewards, and results in policy bottlenecks and suboptimal convergence. And from A3C stability and trading efficiency trade-off, we can see from A3C improves training via asynchronous decorrelation. However, limited global context representation and uh, sensitive to noisy financial signals, which causes excessive portfolio turnover and severe transaction cost penalties, which lead to weak real world uh, profitability. And static clustering is insufficient since clustering reduces dimensionality and high frequency noise, but systemic risk is driven by dynamic asset uh, coupling and correlation regime shifts, which leads to static clustering fails under regime transitions and exposes portfolios to outdated high risk assets. And from QML, strong representation but weak adaptation, since VQC act as nonlinear feature maps in Hilbert space and capture complex nonlinear dependencies efficiently. And it applied in financial DRL. But the key limitation for it is the standard VQCs use static parameters and poor adaptations to test time distribution shifts. And towards adapted and memory driven architectures that dynamic parameterization like QSLSTM and QFWP improves adaptability and parameter efficiency. And fast wave memory that enables state conditioned temporal adaptation and Titan style mechanisms is introduce momentum and forgetting for stability. So the existing approaches fail to jointly address that non-stationary market dynamics, transaction costs, and turnover constraints, and the adaptive representation under distribution shifts. So we propose a structurally robust adaptive portfolio framework, which is Titan QFWP. And our methodology is we can see from part A, the Markov decision process formulation, that the dynamic clustering based trading problem is formulated as a um, MDP defined as state, action, and reward. And let's see from the state space that input constructed from 60-day log returns and apply rolling k-means clustering, which is 10 clusters on S&P 500 constituents. And for the state representation and market integration, we can see from the state vector, which is 42, that includes moving average MA5, MA20, and also 20-day volatility V20, and our cluster sizes and global market signal, which is S&P 500. And action space that address high dimensional continuous control and uh, NICQ scalability constraints. The decision space is protected in a discrete action space, and the action is defined that universe that um, 331 highly liquid assets, which is S&P 500 subset, and action, which is 0 to k minus 1, that select a target cluster. And the capital is equally allocated among assets within the selected cluster. And the reward function is cost-aware optimization that designed with explicit transaction cost and turnover penalty that encourages low turnover portfolio behavior. And our reward design is the formula below that we have the base reward from -1 to 1, and we compute it via normalized return risk ratio that includes transaction cost that 15 basis point and the turnover penalty of lambda equals 0.5. And the limitation of the standard QFWP is that it generates parameter via 2D outer product, which is layer uh, times qubit, and which applies identical rotations across all axes. And this leads to limited expressibility in quantum representation. So we propose a 3D state condition tensor that extend to include rotation axis dimension from x-axis, y-axis, and z-axis. And we encode the state into the transaction cost and also have the layer index, qubit index, and the axis uh, index. And we include the momentum and also the forgetting mechanism into the formula. And we can see clearly from this architecture that we have the QA3C2 as the overall structure, and the Asian part we use Titan QFWP with the forgot and surprise mechanism. And let's talk about the design and the evaluation. So we did a fair representation comparison that evaluate representation efficiency independent to brute force network scaling, aligning trainable parameter counts across models. And we use a baseline complexity classical RL that we have POO of uh, roughly 14,000 parameters and also um, 400,000 parameters for SAC. And the proposed framework, which we have the A3C2 squared plus quantum models that enforce parameter advantage alignment, that quantum models use fewer parameters than classical baseline. That we have model size of classical MLP that which is 6,419, and also have standard VQC, QFWP, and our proposed Titan QFWP of 4,777. And the experimental protocol that we evaluate on 10 random seeds from 1 to 10. And the chronological split is a training set of 2015 till 2021, and the testing period is the 2022 till 2023. And we can see from the results that the first part is our training convergence and stability. That Titan exhibits a more stable learning curve during experiments, showing less divergence compared to classical baselines like PPO and SAC. And the second part we can look at is the statistical testing and performance comparison that employed the Wilcoxon sign ring text during the non-Gaussian nature of the return distributions that demonstrate that Titan QFWP significantly outperforms both PPO and SSE in terms of cumulative returns. And we can see from this table that uh, we did several like annual return, uh, Shortino, max dropdown, etc. And we can see that the Titan QFWP outperforms the benchmark and also um, the classical baseline. And we can see it detailedly with QFWP compared to Titan QFWP that adding this surprise and forget mechanism really did improve like to we can see from the results. And from the out of sample returns that compared to the baselines, we can see that Titan QFWP have 96.7% in uh, in the end of the testing period. And we can see from the cumulative returns and our max drop downs box plot. And we can see when we add the forget and surprise mechanisms, Titan QFWP had a superior uh, performance compared to QFWP, like cumulative returns and also max dropdowns. And the another results we can see from overtrading and the QA3C square framework is the true limitation of advanced DR methods in finance is overtrading. Validated by empirical tracking, the A3C square framework is inherently suppresses erratic reallocations and turnover performance comparison, we can see that Titan QFWP restricts average per step turnover to 22.73%, and standard 2D QFWP achieves 27.73%. That Titan's 3D axis wise control improves temporal stability. And DR baselines stark contracts to wrapper based SAC and discrete PPO. And we can see from this transaction cost uh, sensitivity that QA3C square vs baseline that we can see that PPO and SSC face alpha decay, and it reaches the lowest in 1.4% of transaction fee per trade. And while the QA3C Square family outperformed to the uh, the classical baselines. And we can see from another result is the behavior analysis that decoupling macro and micro. That this is the trade hit rate analysis. And we can see that we did two comparison is one is the absolute win rate, which is versus 0, and the relative win rate that versus the S&P 500 market. And we can see from uh, it is the A3C square family really outperforms the classical baselines. And also we can see that Titan QFWP that outperform um, basically other uh, other architecture that in the QA3C square family. Okay, and we can break it down to see the dynamic factor allocation behavior. That this is the Titan QFWP that in the testing period that we break it down into actual stocks performance, and we can see that in June 2022 it faces a rebound that automatically pivoted to energy and material stocks, and in October 2022 and it rebalanced into high beta semiconductors like uh, LRCX and AMAT. And this is the computational efficiency and hardware mapping. And from the uh, like PPO, SSE, and MLP, we just use CPU only. And this is the training time. And for the quantum part, we apart from CPU, we also did Lightning Qubit to faster the time to compute. And for the discussion and limitation is the sample period constraints because we only evaluate on 2022 and 2023 regime shifts period, potentially uh, biasing result toward strategies that exhibits regime persistence and reward design assumptions that employs a fixed penalty parameters that lambda equals uh, zero point 0.5, which fails to capture dynamic real-world transaction cost and the real-world implementation gap that assumes instantaneous execution at closing prices and evaluates the quantum component via classical simulations, overlooking market impact and physical hardware noise. Therefore, we have the conclusion that the methodological paradigm that frames quantum fast rates as a feature mapping mechanisms for non-stationary prioritizing structural design over sheer quantum advantage, and allocation decoupling that separates macro allocation from micro rebalancing to fundamentally suppress RL overtrading, and stability enhancement that boosts temporal policy stability via 3D spatial updates and forgetting mechanism. So this is my paper presentation too, and thank you for your attention.